All right, so now that chaos has passed, this is again, that was just for prerequisite knowledge for your interest and for completeness. But what's important is that these transfer functions, like the one that we had, so we just wrote V out of S over V in of S, right, for the RC circuit. We know that it was 1 over 1 plus SRC, and that's for the RC circuit, right? And so what we can see here is this. Okay, before I get into this, let's just talk about what poles and zeros are. So I have a function here that's a function of S, right? My transfer function, I'm writing it as some function of S on the top and some function of S on the bottom. So for this circuit, the numerator is just equal to 1. It's not really a function of S, but the denominator is a function of S. It's 1 plus SRC. And so what poles and zeros are is there values that cause this transfer function to either blow up to infinity or go down to 0. So zeros are the roots of the numerator, right? The roots of the numerator being, if I set my numerator equal to 0, I can find the roots or the values of S which cause the transfer function to equal 0, right? So if I do that for this circuit, or sorry, for this particular transfer function, I cannot find any zeros, right? I can't set the numerator equal to 0. 1 will never be equal to 0. So this circuit doesn't have any zeros, but it does have a pole, right? And I talked about this in the previous video. But if what is a pole? A pole is the roots of the denominator, which caused this transfer function to blow up to infinity, right? If I have a 0 in the denominator ever, 1 over 0 is infinite, right? It's going to get huge. And so if I set d of S equal to 0, I can solve for S. I get SRC equals -1. I get S is equal to -1 over RC, and that is the location of my pole in the S-plane, right? Again, we talked about the S-plane last time. I showed that a value of -1 over RC, I kind of have it buried down here, but a value of -1 over RC would fall back in the negative sigma axis here. Again, not important for all that, with all that context. It's not necessarily important. What is important is that this pole directly influences the frequency response, which is what we've seen. And how does it influence it? Well, it influences it that we have a pole at -1 over RC, which causes the behavior that we see in the transfer function. And so this pole is the reason why at a value of 159 hertz, the transfer function starts to drop off at 20 dB per decade. If the location of the pole moved, then I would get some kind of different behavior, which would cause it to maybe fall off at a smaller frequency, or a different one that would cause it to fall off at a larger frequency. So moving the pole around, basically, I can change my R and my C value to change where that pole lies, and that would shift the frequency response curve that we found either to a higher or a lower cutoff frequency, right? And it just so happens that we know that, I mean, it's pretty obvious, right? We found that the cutoff frequency for the RC circuit was 1 over 2 pi RC. So of course, changing these values for R and C in both cases, that's going to change the location of my pole, which is also going to change the location of my cutoff frequency, right? So in all three of these cases, I have different values for R and C. Those would be 3 different locations of this pole, which correspond with 3 different cutoff frequencies, okay? So let's just do another, what do I have on the next slide? Oh, I have this. Okay, so that's going to be another video. So let's just do another quick example. Let me see this one in the textbook. This one is pretty straightforward. They've already written it out in terms of S. It's not necessarily, I guess it does pertain to a circuit. Let me just go ahead and add a new one of my current template. I like doing that. So we have this circuit that they give us. I'm not going to take you through the process of solving for the transfer function. If you want to do that, by all means, get some extra practice. But I just want to show you that we can find the poles and zeros pretty easily of this circuit. So this is a circuit with two energy storage elements, an inductor and a capacitor, when a circuit has two energy storage elements, we would typically expect it to have two poles, okay? So I'm going to go ahead and take a look at this circuit. I'm not sure why they're calling this V out, but they are. They're calling this V out of T, and they're calling this I in of T. So if you're interested, this is SATIQ, the SATIQ textbook, practice problem 14.2, or this is on page 617 if you're interested. Okay, so what they have is they have let's see, let me get the values. 10 ohms here. They have 50 millifarad cap. Yeah, that's a pretty big cap. They have 2 Henry inductor, which is huge. They don't use very realistic values in this book. They do it so that the math works out nicely, which is fine. But if you go through and you find the transfer function V out over I in for this circuit, okay, they have found that in terms of S, that transfer function is 10 times S plus 2 times S plus 3 divided by S squared plus 8S plus 10. Okay, and so from here, finding the poles is trivial, right? The poles and the zeros. The zeros are incredibly trivial. To find the zeros, I just have to basically look at the numerator and say, oh, okay, S equals -2, that's a 0. S equals -3, that's a 0. For the poles, I could use the quadratic function or something, or the quadratic equation, or maybe not the quadratic equation, but I can use any number of things to factor this, but the quadratic equation is probably your best bet. And I can find that I have poles. If I were to carry this, I'm trusting the book on this. It's S equals -1.55 and S equals -6.45. Okay, so those would be the 2 locations of my poles. This would be the 2 locations of my zeros, and that is derived by just setting the numerator and the denominator, sorry, I said that backwards, the numerator and the denominator equal to 0 and solving for my values of S, right? That's what I do when I use the quadratic equation. I'm looking for the roots. So here I look for the roots of the denominator, the roots of the numerator, and I found my poles, my zeros up here, found my poles down here for this particular transfer function. Okay, and so again, this might even be more complicated than anything we're going to see, because this would be a very complicated transfer function that has 2 poles and 2 zeros, and the Bode plot would get pretty ugly. But I did want to just overview all this to show you what's happening. These poles and these zeros have associated behavior when we do the frequency response. And so that's what I'm going to show you next, is that we can take all these different factors and we can basically build a transfer function out of these different factors, or we can decompose a transfer function into separate factors, which is what I'm showing here. Different factors, I'm calling these factors F1 of S, F2 of S, and if I just multiply them all together, I get one big transfer function. And we're going to use log rules to show that you can just add all their effects to create the Bode plots. Okay, so I'm going to go ahead and end this video here. Again, the key takeaway of this video is just that if I have a transfer function in the S domain, all I need to do is set the numerator equal to 0 to find the values of the zeros, and I have to set the denominator equal to 0 to find the values of the poles. Okay, so I'm going to go ahead and end this video, and in the next video we're going to talk about factors of these transfer functions, and then we're going to get into what the behavior of these factors look like. So this is all just laying groundwork, okay, for what we're actually trying to get to. So I'm going to end this video.